Okay, good afternoon. Welcome to
Another 1036.
Math 1036. So today we're going to talk a little bit about some of the information on the coronavirus and the way it's presented. And in particular, we're going to talk about the difference between seeing things on regular graphs that you see on some of the presentations that have been on plots, what are called like log plots or something. Have you seen any of those logarithmic plots?
No.
Have you?
Yeah, some of them.
Some of them? Okay. All right, so first of all, let's talk about what an exponential curve is. Do you know?
So it's
Right.
something that follows a certain pattern from, so like y equals x squared would be an example. So it doesn't increase at a constant rate, it kind of goes up like this, something like this.
Well, that's an interesting example. That is actually called a polynomial rather than an exponential. But you're definitely right that something like y equals x squared does go up really fast. It starts at 0, 0, then it's at 1, 1, and then 2, 4, 3, 9, 4, 16. So that does go up really fast. But exponential curves are a little different than that.
They follow the power of, like, say if you had 1 on this graph, would it go 2 to the first power, and so on? It'd be like an exponential.
Yeah, like something instead of y equals x squared, it'd be y equals, say, 2 to the x. And where does that start when x equals 0?
It starts at 1.
Starts at 1. And how about at 1 when x equals 1?
Goes to 2.
Goes to 2.
Then it goes to 4. Goes to 8.
Yeah, so if we look at it here, it does look a little bit different than x squared, although on a small plot it's actually not so easy to tell the difference. What are some properties that these exponential curves have? Do you know some properties that they have?
Well, they get large quick.
Okay, yeah, they certainly can get large very fast. But x squared also does get large fast,
Yeah.
right?
They get bigger than any polynomial function.
Ah, okay. So by getting large fast, they actually can get bigger. They get bigger than polynomials.
Okay.
And they're at least they're always positive is one thing, unless you sort of mess it around and instead of like you do x equals 2 to the y or something, but usually they're always positive.
Okay.
So it would extend sort of this way, like.
Yeah, so that's a great point. So when x equals, so we said that this is 2, 4, 1, 2, 0, 1, and then where do you think it would go to at -1?
2 to the -1 is 1/2.
Yeah, 1/2.
So then 1/4 and 1/8.
Yeah,
so it gets almost that.
Goes like this. Yeah, and we can see, like with our example here, 2 to the x and x squared. Well, at 2, 2, they're actually the same, right? 2 squared is the same as x squared. At 3, we get 2 to the third power, which is
8.
And x 3 squared is
That would be 9.
9. But like if we go up to the 10th, 10 squared is 100, but 2 to the 10th is
1024.
so much larger.
Yeah.
Right, but you might think, well, maybe it doesn't eventually get bigger than x to the 100th or something like that, but actually it does.
It does.
Yeah, so it's actually pretty neat. And so, because these curves get big so quickly, sometimes we don't look at them the way we look at normal the way we're used to looking at graphs, and instead we look at them through what are these logarithmic graphs. So I want to talk about what those are, and then show how they can be used, looking at how the coronavirus spreads.
Okay.